Okay, good afternoon, everyone. Let's start. As you know, today we have, or you can see in the slide, today we have a discussion session. We are going to solve some questions from the optional homework that we have selected for you because we consider that they are good, let's say they are typical questions that you can find in the final exam. So far, we have released 5 homeworks, if I'm not wrong, and we have released the solution of 3 of them. Early next week, we will release the solution of homework 4 and homework 5, and we will also release homework 6, that is memory hierarchy cache, virtual memory, and also I think there is some question about systolic arrays. So we are going to start now with the first optional homework. This is optional homework 1, and you might remember that there were 2 questions in this homework. Okay. Yeah. So, yeah. So for now, what I'm going to do is reading the question and reading the solutions and talking a little bit about them. If you have any questions, I guess that you had enough time to read the questions, the solution, try it yourself. So I think this is going to be easy. So the first question, DRAM refresh, says a new supercomputer has a DRAM-based memory system with the following configuration. We have a total capacity of 1 exabyte. The DRAM row size is 8 kilobytes, and there is a retention time, minimum retention time in these DRAM cells that is 64 milliseconds. So as you already know, because this is something that Professor Mutlu explained in the beginning of the course, DRAM rows need to be refreshed from time to time because they are, DRAM cells are capacitors, and these capacitors are so small that they leak the charge. So from time to time it's necessary to refresh in order to not lose the data that we have stored in them. So the very first question, part A, is very simple. How many DRAM rows does the memory system have? So as you know, the DRAM memory is divided into subarrays, and each of these subarrays contains several rows, many rows, right? And rows of DRAM cells. We know, because that's what the question says, that, and this is also a typical value, the size of this row is 8 kilobytes. So the total number of cells, as you can guess, is 8 times 8K, right? So, as you can read here, 1 exabyte is 2 to the 60th, and the row size is 2 to the 13th. I think that this doesn't need too much explanation. So this is 1 exabyte, and this is 2 to the 3rd times 1 kilobyte, that is 2 to the 10th. So that's why we have 2 to the 60th, 2 to the 13th, and if we divide the total capacity between by the size of the row, we will get these 2 to the 47th rows. That's clear, I guess. No questions. Okay, perfect. So how many DRAM refreshes happen in 64 milliseconds? So this is also easy because, as you can read in the question, the minimum retention time is 64 milliseconds. So every DRAM row is refreshed once every 64 milliseconds. So what's the total number of refreshes? It's 1 refresh per DRAM row, right? That's what the answer says. Number of refreshes is the number of rows is 2 to the 47th. The third part is a little bit more complex, especially because if you try it yourself, you had to take a look at these data sheets that we have in the, we uploaded to the wiki. And let me show it to you. Here we are. So the question asks, what is the total power consumption of DRAM refresh in 64 milliseconds? And give us some hints, right? It talks about some current, that is the current that is needed to charge the DRAM cells, this IDD, so-called IDD, and well, we have to compute the power consumption, so not only the current, but also the voltage we will need. That's VDD. This voltage can also be found in the data sheets. So what's the total power consumption that is needed for refreshing the entire memory? Well, as many refreshes that we need, that is the number of rows, times the power that we need to refresh every row. So in order to calculate this P refresh, you have to go to the data sheet and you will find this DD5B. So observe here, the power needed for the refresh of one row is DD5B times VDD. And these values can be found, so for example, for this DDR3 memory, you can find this value. You can also find this value of VDD, and you can compute this P refresh. So after that, the total will be this number here, as you can see in the, can you see it or not? Why don't you say anything? Okay, right there. Okay, and then afterwards, last part is, what is the total energy consumption of DRAM refresh during a day? So we already have the power. As you know, energy is power times time. Time is 1 day, so 24 hours times 60 minutes times 60 seconds, and you will obtain this total energy per day. You have any questions? No. Oh, you have one question?
Are there any machines that actually have 1 exabyte of memory?
Well, probably, or very soon we will reach that capacity. So this is like the road to the, so-called the road to the exascale. In, let's say, very few years, I think it's, China has as a goal to reach this in 2020. And they will have the first supercomputer with 1 exaflop. So they will also need 1 exabyte at least. Okay? Any other questions? Okay, let's take a look at the second one, main memory potpourri. Yeah, this is also, it's very interesting because it teaches us how to reason a little bit about typical main memory issues. So in this machine, we have 4 gigabyte DRAM, and each row is, as is the typical value, is refreshed every 64 milliseconds. It's important for you to note what this note says. This question is open-ended, right? This you might find sometimes in our homeworks, or even in an exam sometimes. So the most important thing here is to reason and to give a thoughtful answer, let's say. So these are some possible answers to these questions. Maybe you can have different answers, and it's also possible to have some discussion if you want. Okay, so the part A says the machine's designer runs 2 applications, A and B, each run alone on the machine. Although applications A and B have similar number of memory requests, application A spends a surprisingly larger fraction of cycles stalling for memory, so larger fraction than application B does. What might be the reasons for this? So very briefly, to remind you how the memory is built, right? Let's say this is part of the DRAM memory. This could be a subarray. And in this subarray, as you already know, we have many rows of DRAM cells. Let's draw each of these little circles is one of these DRAM cells. So in here, next to the subarray, what we have is many sense amplifiers. And we have one sense amplifier for each of these bit lines. This array of sense amplifiers is the row buffer. So current DRAM memories usually, typically use nowadays one policy that is called the open row policy. This simply means that the first time that you want to access this row, the row is loaded into the sense amplifier. Each of the DRAM cells goes to the corresponding sense amplifier, and this row here remains open until someone, maybe the same program, want to access a different row. So that's what is called the open row policy. And the question is asking, question A is asking why application B takes so long. So if you take into account what I just explained with regards to the row buffer and with regards to the subarray, you can figure out this answer. It's likely that application A, so in the case, yeah, exactly. Application A takes larger fraction of cycles than B, right? So it's likely that A, memory requests are row buffer conflicts. This means that A accesses this row, and the row is loaded to the sense amplifier, and then next it accesses the next, a different row. So we have to remove the first row from the row buffer and then load the second row and so on. So there are many row buffer conflicts. This means that consecutive accesses need to read from different DRAM rows. So that we will have many row buffer conflicts. And probably in the case of application B, there will be many row buffer hits. So that's a possible answer why application A takes longer than application B. Do you have any idea about other possible reasons? Recall this is homework 1, right? This week and last week, Professor Mutlu explained caches, and you already know that there might be, so cache is a memory that is closer to the processor so that the memory access is faster, and you already know that there are cache misses, cache hits. We could have a similar behavior for these two applications if we have many cache misses for application A in this case, and many cache hits for the other one. Okay, part B says application A also consumes a much larger amount of memory energy than application B. What might be the reason for this? And the reason is the same, right? The reason is that there are many row buffer conflicts for application A, and a row buffer conflict takes more energy than a row buffer hit. Why is that? Well, it's simply to understand that the row buffer conflict requires more operations, right? Because you need to pre-charge, which essentially means to replace the row that is already in the row buffer, and then activate, that is moving the new row to the row buffer, and then read and write. But in the row buffer hit, we only need to read and write because the row is already in the row buffer. Is it clear? And part C, when applications A and B are run together on the machine, application A's performance degrades significantly, while application B's performance does not degrade as much. This is also something that Professor Mutlu explained in one of the first lectures. He talked about memory schedulers, and he explained that also because of this reason that these DRAM memories today have this open row policy in order to improve the performance and in order to save energy. It is typical that the memory schedulers, the memory controllers implement this scheduling policy, first ready, first come, first serve. This means that if we have, let's have here our memory controller, and this memory controller is receiving requests from two applications, A and B. The memory controller is going to prioritize, let's say this is the DRAM. The memory controller is going to prioritize those memory requests that are going to hit in the row. So that's why it is called first ready, because if the row is already here in the row buffer, it's already open, the memory controller will prioritize those accesses, right? So that's why A had many row conflicts, so the memory controller tends to prioritize memory requests from application B. Is it clear? Yep.
Could it be possible that the energy consumption of accessing the memory is different if you access different locations in the memory, or should it be safe?
Is different. So the memory consumption, depending on the row that you're accessing, it will be different if the row is open or the row is closed. There shouldn't be any significant difference depending on what's the position of the row, okay? But yeah, there might be, these guys know better than me for sure. But this is, let's say, something that would be more related to the research that they do in the department. So let's say that in the theoretical assumptions, the energy is exactly the same, and you will have different energy consumption depending on the fact that the row might be open or not. Okay? Okay, any other questions? Okay. Part D says the designer decides to use a smarter policy to refresh the memory. A row is refreshed only if it has not been accessed in the past 64 milliseconds. So why can the designer think about this possibility? Well, because if the row is open, if we are here, this is the row that we are reading in the row, it's already in the row buffer. When the row is replaced, when the application needs to access another row, this row here will be moved back, will be pre-charged to the original row of cells, of DRAM cells. So as soon as the row is replaced and is back in its original row, it is completely, these cells here are completely refreshed. So the charge of the capacitors is full. So the good thing is that it wouldn't be necessary to refresh. So let's say that the refresh cycle, it's happening right after this row has been pre-charged. It wouldn't be necessary to refresh this row because it has just been accessed. So the corresponding cells have all the charge. So there's not time enough to have charge leakage. So that's the reasoning behind this proposal here, this smarter policy. And then this says, a row is refreshed only if it has not been accessed in the past 64 milliseconds. What do you think? Do you think this is a good idea? Why or why not? Well, I think I just explained this. So the answer says this can reduce refresh energy significantly if a large fraction of the rows in memory contain data and are accessed within the 64 millisecond refresh window, as these rows do not have to be refreshed explicitly. Okay? Yeah. And part D says, when this new refresh policy is applied, the refresh energy consumption drops significantly during a run of application B. In contrast, during a run of application A, the refresh energy consumption reduces only slightly. Why this is possible and why or why not? And it says, yeah, it's possible. Why is possible? Well, this depends on how many rows each of the application accesses, right? So for example, in this case, application B has a large working set. So there are many accesses to many different rows. So many of these rows are refreshed very frequently. So they don't need to be, refreshed, are accessed. And for this reason, they are pre-charged. So there is no need to refresh them additionally. It's not the case for application A, where the working set is much smaller. So only very, very few rows are being read and in consequence pre-charged. So the rest of rows that are not accessed still need to be refreshed. Is that clear? Okay. So now we are going to continue with one question from homework 3. I'm pretty sure you already know this, and probably you haven't even solved it. We're going to have some discussion about it. So this is question 2, the MIPS ISA. And yeah, this question has 2 parts. In the first part, it's warm-up, computing a Fibonacci number. So this is about writing MIPS code to compute the Fibonacci number. And as you know, this is the expression for the calculating Fibonacci number. And here you have a high-level language code, C code, to calculate this Fibonacci number. So as you can see, we have 3 variables. We have A originally is equal 0, B is equal 1, and this is C, that is equal A plus B. And then we get into this while loop that will be repeated n-1 times. And in the loop body, what we have is we first compute A plus B and store the result in C, and then we store B in A and C in B. So finally, we decrement this counter n, and we repeat the loop while n is greater than 1. So here there are some assumptions, conventions to write our code. But let's say that the most important thing for now is that the argument n, that is this counter here, is going to be stored in register 4, and the result C, this C here, is going to be stored in register 2. Then there are also some register numbers, for example, for Kali save temporary registers. We're going to need these because, as you will see in the code, this Fibonacci computation is going to be in one function. Then we have the stack pointer. We're going to need the stack pointer, as you might remember, to save the temporary registers. And we also need one return address because, as you remember, every time that we call a subroutine, we call a function, we need to store the return address somewhere, and the return address is the return program counter, and this is typically stored in register 31. So let's take a look at this code. Yeah, let me do something so that you can see the code. So the very first thing that you find in this function, in this Fibonacci function, is that, well, this is the beginning of the function, and the very first thing is storing the registers into the stack, because some of these registers might have some values that are used for the main, are useful for the main function, but these registers might be needed by the function itself. You know that the number of registers in every computer, but especially in the MIPS computer that we have studied here in this course, it's quite limited, so it might be necessary to use some of these registers that are already being used by the main function, the caller function. So that's why the first thing that we have to do is saving the registers, in this case, registers 16, 17, and 18. 17 and 18. We store them in some part of the memory that is pointed by the stack pointer. And right after that, we initialize the registers with some values because we are going to use them. Okay? You had one question? Excuse me, you had one question?
Yeah, well, I have just one simple question initially, but it's not relevant to what we're doing right now.
Oh, okay. Then you can ask maybe later in the break.
Yes.
Okay, so observe that, well, let's say that this is the function call. So this is the beginning of the function, right? After starting with the function, we have to store some temporary values in this stack. And right after that, the first thing that we do is this first C equal A plus B. So this is an addition. We store C in register 2. In register 6, 17, and 18, we have A and B. So this corresponds to this first C equal A plus B. And now, the next thing that we are going to find is this while loop, right? So in the while loop, the first thing we do is checking the boundary condition. So here, this is n must be greater than n than 1 to get into the loop body, and this is what we are doing with this set on less than immediate. We compare this register 16 that contains n, we compare it to 2, and if register 16 is less than 2, then register 3 will be equal 1, right? Observe that if it's equal 1, it won't branch, right? So it will go, so sorry, if this is equal 1, it's not equal to 0. So if it's not equal to 0, won't take this branch, so it will go to the loop body. And what do we have in the loop body? Well, the first thing that we have is, again, add to 17, 18, that is C equal A plus B, corresponding to this instruction here. Then we store B in A. So that's why what here we are essentially doing is adding B plus 0 and storing it in A, in register 17. We do the same to store C in B, and after that we decrement -1. This is immediate addition -1 to decrement N. Right after that, we have this unconditional branch, this jump instruction, to start again and evaluate again the value of the content of register 16 that contains N. So we repeat this as many times as needed. When 16 16 contains N. When 16 is lower than 2, then this will be 0, and then here we will take the branch and we will until this down here, and we will finish the loop. And the very last part that you can find here in the code is this restore, because remember that in the beginning what we did was storing the content of these temporary registers in the stack. Now, right before leaving the function, we have to restore the contents of the registers. Yeah. Do you have any questions here? Go ahead.
In the labs, we were using those other names for the registers.
Yes.
A0, but S0.
Yeah.
Can we put it in the test, or do we have to know the exact?
So in the exam, what I recommend you to use is to do the notation that the question itself is using, right? So in this case, we are using the numbers. In other case, you will use the error something. But as you know, and actually you can check in the slides, they have the same meaning. Yeah. Yeah. Go ahead.
Are we saving the return address inside the stack just as a formality, or why is it done? Because it's not overwritten.
Yeah, exactly. It's not overwritten. This is just a convention. So you can save it in case you might need to use this. But this is just a convention.
But it would not be wrong.
It could not be wrong if you don't overwrite it. Okay.
I thought my question before was about the name of the registers, but the way we're using is basically just a convention. You can use any for any purpose.
Well, I mean, usually if you have in the final exam some similar question like this, we will probably give you this kind of convention. If we don't give it to you, you are not required to know exactly this, but you can check in the slides and you will see what are the typical registers that are used for some particular purpose. Okay?
But there are these preserved default registers and the ones that are not preserved. So basically, it's just a convention we use to express, right?
It's just a convention, exactly. I mean, if one question like this asks you to stick with some convention, you should stick. It's not more than that.
I don't understand why you need to store the values of the register first in memory, because register 16 to 23 are calling safe. Doesn't mean that the call don't can store important values there. Or why do you have to store the values in the memory, the first part and the last part? Why do you need to do them on the stack?
So they are Kali safe because they are safe by the Kali, right? This doesn't mean that the caller cannot use them. Before calling the function, before calling this Fibonacci function, we have some other function, maybe a main function that calls the Fibonacci function, and this main function might be using these registers. If we have this convention and every time that the function is called, we store these registers in the stack, we are on the safe side, right?
So it's just for safe.
Yes, exactly. It might, I mean, this, keep in mind also that you write this Fibonacci function just once, right? And then you might need to call it from different place in your main program or in different programs. And sometimes you might be using these registers, sometimes not, okay?
Yeah. So would it be possible, in this case, we know you've got a variable, so we could just use the caller, say, registers, and then you don't need to, then you don't need to say the content of those registers on the stack because they're caller, say, so in the calling we can just use them as we please.
I mean, it's, your question is related to his question. In some particular situation, you might be able to do that, but the thing is that you are going to write this function just once. You just want to write this function once. And you know that in this function, there are 3 registers that are used, that are 16, 17, and 18, and you're going to operate using them. It might happen that sometimes you're really using these registers, other times not. But it is safe to have this convention that those registers that are going to be used by the function are by default safe in the stack. And this way you avoid any possible overwritten.
This just prevents a bug in case anyone does not support the convention of caller safe and calling safe function.
Say again?
Because we could just use as for convention stated in the exercise, we could use it as a register for making it.
Yeah, sure. But how do you know that these have not been are not in use by?
We can't know for sure, but by the convention they should be caller safe. But because we don't know for sure, we just do it.
Yeah. Okay. You had another question?
Yeah. During the semester we saw MIPS as well as LC3. We have to like know them both really well, or is it like more focused on MIPS?
Well, I think that you should know really well what Professor Mutlu has explained in the lectures and what you, and ideally also what you have in the optional homework. Yeah, it's a reasonable answer.
We mainly see exercises which they always talk about MIPS. We see MIPS the whole time. So
there are also many, several lectures where we have talked about LC3B, and also there are a few exercises in the homework. Yeah, in this homework 3, for example, there are at least 3 or 4. Sure.
So what do you mean exactly about knowing about instructions? You're asking about like semantics of instructions. It's something that we should provide in the exam.
okay, yeah, exactly.
So you should just know, like, you should just have general understanding of how assembly programming moves.
Okay, but like, so we would need to know like the what parameters LST or MCI, or like more automatic parameters.
No, so usually we clearly define. So if, for example, an instruction defines like add.
Can you speak up?
Yeah, sure.
Yeah. Actually, you can use this one.
Yeah, so basically, when we provide the instruction definition, we also provide the semantics. So we tell this register is the destination register, and those 2 are the source registers. And basically, the exam should know exactly what instruction is doing what.
Yeah, it's on if you want to switch it off. Okay. Shall we continue, or do you have any other questions? Okay, let's go to part 2. And here, MIPS assembly for rep mob SV. So here we are asked to write some code, some MIPS code that is going to do essentially what one x86 instruction does. And this is x86 instruction is this rep mob SV. The mob SV part means that we are moving bytes, and the rep part means that this is going to be repeated several times. This instruction has 3 registers. There is one count register, this ECX, and then we have one source register and one destination register. This source and destination are 2 pointers to 2 different arrays, and what this operation does is for several times, and this number of times is the content of this register ECX, what we do is copying byte by byte from the source array to the destination array. And after each of these copies, these 2, ESI and EDI, are incremented. So part A in this question, sorry, what's wrong here? Okay. Part A in this question is asking about how to implement this in MIPS. So, yeah, this actually has some similarities with the first part. In summary, what we are going to have here is, if we, let's say, we write the high-level language code for this instruction, we would have something like this, right? ECX. Greater than 0, because ECX is the counter, right, where we have the total number of bytes that we need to copy, and this would be something like EDI ECX equal ESI ECX. This ECX would be like our counter and also index to these arrays, ESI and EDI, and after every iteration we decrement. So this would be like the, let's say, the high-level language code to implement this rep mob. And here what we have is the MIPS code. There are, we assume that ECX is stored in register 1, ESI is in register 2, and EDI is in register 3. The first thing that we do is checking what's the value of register 1, that is the value of our counter, and if it's not 0, we will go to the loop. And in this loop, as you can see, we load 1 byte, we store this byte in the corresponding memory position. These memory positions are determined by register 2, that is ESI, so the pointer to the source array, and this one, register 3, is the pointer to the destination array. So right after that, we increment register 2 and register 3 to point to the next byte, and we decrement register 1 that contains ECX, so it contains our counter. And after that, we check, we check what's the value of register 1, if it's still greater than 0. If it's greater than 0, we branch to the beginning of the loop body. If it's not, then we go to the rest of the code, to the following instructions. So it's very similar to what we did before, and I think it's quite easy to understand. So don't know if you have any questions. So let's continue and go to part B. In this second part of the exercise, it says, what is the size of the MIPS assembly code you wrote in A in bytes? How does it compare to rep mob SV? And it says, note, rep mob SV occupies 2 bytes, right? So this Intel x86 instruction occupies 2 bytes. And the question is, how many bytes occupies in memory this code that we have just written? Well, as you know, in MIPS, every instruction is stored in 4 bytes. And if you count the total number of instructions, this is 7. So the total size of this code is 28 bytes compared to the 2 bytes of the original instruction in the x86 ISA. Let me finish with this question and then we take our 15-minute break. Is that okay? We will finish very soon. Part C says, assume the contents of the x86 register file are as follows before the execution of this instruction. And these are our registers, the content of these registers. And it says, now consider the MIPS assembly code that we have just written here. How many total instructions will be executed by your code to accomplish the same function as the single rep mob SV in x86 accomplishes for the given register state. So the given register state is this one here, and as you can see, this register ECX has this value. This is hexadecimal representation, but if we convert it to decimal representation, is this number here. So because this ECX register tells us the number of times that the loop, this loop here, is going to be repeated, the total number of bytes that we are copying, and the body of the loop has 6 instructions, the total number of instructions executed in this case is 6 times the value of register ECX, plus 1, because remember that in the beginning of the loop we had this BEQ instruction. So this is our total number of instructions executed for MIPS compared to one single instruction that will be executed if we have an x86 ISA. The last part, part D, is exactly the same. So the question is exactly the same, but the contents of the register file in this case are different. And if you observe the value of ECX in this time, it is 0. So if it's 0, we are not going to enter the loop, right? If it's 0, this ECX is 0, this register 1 is 0, so we don't execute this loop body any single time. So the total number of instructions that are executed in this case with these contents of the register file is only 1. It's only the first BEQ instruction that you have in the code. Is that clear? Okay, let's take the 15-minute break until, yeah, and we will continue after that. So we're going to continue now. Yeah, and the next, Hassan is going to solve questions 3 from homework 3, this question about the data flow program.
I guess you can hear me, right? Okay. Okay, so we will continue with this question on Thomas' law, and I think Professor Mutlu already showed some example during the lectures, but I think this is an important concept that we can go over once more. Okay. So I'll just quickly read the question. So this is kind of a question that doesn't require too much computation or too much knowledge exactly about how the algorithm is working, but it's asking more about the overhead and how many functional units or comparators you need in your design. So it basically defines those properties where you have 8 functional units and 32 registers, and each register is 64 bits wide. And then you have 16 reservation stations entries per functional unit. And so basically you have a reservation station for each functional unit, and you have 8 of those, right? And each reservation station will have 16 entries. So this will basically look something like, let me see, oh, this is so ugly. Yeah, so basically it will look like this, right? So you have some functional units here. Okay, I can't draw very well, but you have 8 functional units in total, and each functional unit will have its own reservation station. Okay, and we have 16 entries in total per reservation station, and there are as many reservation stations as functional units, right? Okay, so this is so far what the question told us. And also there are 32 registers, 30 architectural registers. And then again, importantly, each entry in the reservation station can hold up to 2 source registers. So basically, this is like, so this is exactly the same reservation station that we saw, that we had in the slides during the lecture. Basically, here we have 2 source operands, right? And then it has separate tag fields for each source field. I guess you can see it. And then separate data fields. Yes, so it looks something like this. And the question is asking about how many tag comparators are there per reservation station entry. So if we go back here, so in a single reservation station entry, we have two tags, right? Because we have 2 source operands. And so we will need a comparator for each tag for each functional unit, right? Because at this, in the same cycle, each of those 8 functional units can produce a result, and this result needs to be compared with each of the tags in the reservation station entry, right? So we have 2 tags here, and we have 8 functional units. So basically, it means that we will need 8 multiplied by 2 times tag comparators. Okay, is it clear? Yeah, so basically, the result coming out from this functional unit will be compared against this tag and this tag. So same for this functional unit, right? So it will need to be compared against those 2 tags. And the same is true for all functional units. Basically, we'll need 2 comparators per each functional unit. Then the answer is 8 by 2, which is 16 tag comparators per reservation station entry. Okay, is it clear? And then the second question, B, is what's the total number of tag comparators in the entire machine? So this is kind of like tricky, because if you just think about reservation station entries, you may not take into account the RAT, register alias table, right? Because it should also have some comparators, because when you calculate the result, you don't need to only update the reservation station entries, but also the register alias table, which is not shown here. But if I draw this, the register alias table will be basically, it will have 32 entries, because we have 32 architectural registers, right? And then it will have data field for each entry. It will have some tag field, right? And it will also have some valid bits. Okay, so basically, we also have some comparators here, right? So 1 comparator for each tag. And then it will be again multiplied by the number of functional units, because in a single cycle, we will need to compare those tags against each of the results coming out from the functional units. Okay, so if we accumulate everything together, so we have 16 tag comparators for each entry, right? And we have 16 entries in a single reservation station. And then we have 8 reservation stations in total. Okay, so those are the total number of tag comparators for the reservation stations. For the register alias table, we'll also need 32 multiplied by 8 comparisons. So here 8 again is the number of functional units we have. Yeah, and you can calculate this. Okay. What is the minimum possible size of the tag? So this depends on how many entries you have in your all reservation stations, right? So as we show here, so you may have in a single reservation station, you may have 16 entries for which you can do some computation and produce a result, right? So so you can remember this from the slides that we address those as A, B, C, and etc., right? So basically those are the addresses of those entries, and you need addresses as many as the total number of entries you have in your system. So there are 16 entries in a single reservation station, and we have 8 reservation stations in total, right? Which makes 128. So this is the number of address, this is the address space that we should be able to address, right? And basically this is equal to 2 to the 7th, and this means we need 7 bits as a tag to be able to address or refer to all reservation station entries. So the minimum is 7. Of course, you can have more than 7, but then you'll have some redundancy, right? Some useless bits. I guess nobody has any questions. Okay. And then what is the size of the register alias table in bits? So the register alias table is, it should look something similar to this thing here that I draw, right? So we know the tag that should be at least 7 bits. And then the data is given in the question. So the architectural registers are 64 bits wide. So then per entry, we will need 64 bits. And then we should have at least some valid bits, right? So for a single entry, we will have 72 bits. And we have 32 entries in total. So it will be 72 multiplied by 32. And I guess, so just let me check if I'm missing anything. Yeah, I think, yeah, that's it. So this is the total storage needed for the register alias table. And then the last part is, what's the total size of the tag storage in the entire machine in bits? So it only asks about tag storage right now. So we should include the tag storage in the register alias table as well as in the reservation stations. So in the reservation stations, we have 2 tags per entry, right? So it is 14 bits because we know the tag is 7 bits. So it is then 14 multiplied by 16, because we have 16 entries per reservation station, and there are 8 of them, right? So this is the tag storage for the reservation stations, plus the tag storage for register alias table, which is 32 multiplied by 7, right? We have only 7 bits in each entry, okay? I guess, is this correct? Is the total minimum size of tag storage in the entire machine in bits? Okay, yeah. Okay. Everything clear? I think that this was a relatively simple question. Now let's move to a more interesting one. It's about data flow. Do you remember data flow? So it was kind of early in the lecture. I think it was on the, I don't know exactly which week, but it has been a while. Probably you are not looking at data flow machines. So this question asks for Fibonacci function implementation, right? And it gives you some nodes here that you can use, such as addition and greater than operand, then copy and branch. So you are allowed to use only those, and also you can use constant inputs to feed to your nodes. And that's it. So using those nodes, you will need to implement Fibonacci. So just a quick reminder about Fibonacci. So it is a like series of numbers which goes like 0, 1, 1, and then 2. So basically each number is, except for F0 and F1, each number is the sum of the previous two numbers, right? So basically the next number is 1 plus 2, and the next number is 2 plus 3, and then 8, then 13, and it goes like this. So F0 is 0, and F1 is 1. So this is by definition. And the rest is Fn minus 1 plus F minus 2. And so you can implement this in a recursive manner, but it is, I guess, more difficult in data flow. So just the iterative version is, I guess, easier, where you will just basically do it as I showed here. Start with 0 and 1, and then the next number is the sum of the previous two numbers. So here, in this type of questions, I guess it makes more sense to start simple, like to start with part of the question, but not to like design everything, the entire data flow at once. So you should do it really step by step. So the first step should be, in this question, making the data flow engine work for n equals 0, right? So for n equals 0, your data flow engine should return 0, right? Because this is how F0 is defined. Okay, so let's start with some input n. So I will write it here. Okay. So we have n. So we'll assume that this is 0, right? But it could be anything. So let's assume this is 0. And so the first thing we will need to do is to compare this against 0, right? And basically, here we will try to make this work only for the case where n equals 0. But still, we will need to compare this, right? And then if this is equal to 0, basically what we will do is, so I don't want to connect this directly because we will do something else later. So I will do a copy here in advance because we will copy this n somewhere else. But okay, let's do it like this right now. Okay, so we compare. So we know that here the result will be false because n will be equal to 0, but not larger than 0. And then, so this will generate some flag, right? So let's also copy this flag. And then the next thing we will do is, so if the result here is false, we'll need to return 0, right? And then this is simple. So we'll just basically put here a branch node and then feed this in here. And if this is false, so this is the false path, right? 0 here, which is hard-coded, should be directed to the output, right? And if this is true, you should just consume this, but do nothing, right? So we just consume the 0. And then the rest of the logic will do something else. Okay, so basically, so here, just with this data flow, it is working fine for n equals to 0 case, right? If it's 0, it returns 0. If it's not, if n is not 0, it is not doing anything meaningful. Okay, so the next step is making it work for other values too, right? So for n equals 1, it should return 1. So we should do something else. to implement that case. So let me put T here to indicate the true path. So the next thing we will do is, so since we here check the first iteration, we will need to decrement n if it's larger than 0, right? And then continue iterating. Okay, then we already have the copy node here. So we will copy this to a branch node. And then this branch node will be controlled with the same flag here that was generated previously for n, right? And then basically, if this is false, right, we should do nothing about, with this n which is forwarded here. Right? We should just consume it. But we shouldn't do anything because it's already 0, so the function should be terminated at this point. So the false path, in this case, is ground. And if it's true, on the other hand, we should subtract 1 from n and do the next iteration. So this is -1. And then basically, we will need to compare this n-1 again against 0, and then see whether it's now equal to 0. So we already have a comparator node here, but so I will do another one. So I'm not sure if this will be possible to reuse this. Even if it's possible to do that, it will be too confusing to understand. So I'll just create a new one because this is hard-coded to this output logic here, right, which is receiving 0. So I'll just duplicate this and basically, so this will be n-1 right here, which is coming. So this is n-1 in this case. So let's copy this again. And then compare this against 0. And then this is basically the new flag, which will be used for all iterations except the first one, right? So for the first iteration, we will use the, yes?
Can you quickly recall how the branch node works? I don't get it.
Yeah, sure. So branches, so it has 2 inputs, right? So 2 inputs should be valid, and it outputs either from the false path or true path, right? And basically, so one of the inputs is the flag, and one of the inputs is data. So if flag is true, the data goes to the true path. If flag is false, data goes to the false path. So the token is generated only on one of the output paths in the branch node. Is it clear? Okay. Okay, so we do this, and then now we'll build our like this addition operation here, which adds together the last 2 numbers in the sequence. So for that, we will need another control node here, another branch node, which will be again controlled by the same flag. So from now on, we'll always use the same flag, but okay, so we'll also have some adder node here. And for n equals 1 case, we'll just need to add together 0 and 1, right? So we know that. So for now, let's just hard-code those values. So I will draw a 0 like this. And we can also draw 1 like this. Is there anything we're missing? Okay, so I don't think so. So you can ignore this branch for now. We will connect this later. So let's just consider n equals 1 case right now. And basically, this result should be forwarded to out if branch. So we have another branch here. This is data, and this is control that's getting. This is the true pad. This is the false pad. And this false pad, sorry, it's kind of ugly, but this false pad should be connected here to the out in this case. So basically here what happens is, in the first iteration, if this flag here, if this comparison results in false, the output will be produced from here, right? And then the rest of the data flow engine will not be active because it won't have any tokens here. So I'll show you a quick example of how it works with some random n number. But when in the first iteration, this comparison generates true, then we won't be using this output logic anymore, right? So the output will come from here. So for example, for n equals 1 case, this will generate this will generate true, right? And then this value will just be consumed, and then this true will go here, and then this will cause n-1 to be generated, right? If this was false, n-1 will not have been generated because it's grounded here. Okay, n-1 is generated, and then it's forwarded here, right? And this is basically the sum of 1 and 0, which is forwarded to the out. Okay, so I think now we have it working for the two cases, 0 and 1, which were the like hard-coded values for Fibonacci sequence. And now we'll just make it like work with any arbitrary n. And for that, basically, we'll create a loop where this result is forwarded on the true path back to this addition logic, right? And then this is basically, so this will need to be connected here. But we'll need to forward the same value to this branch logic 2, because this will be the n-2, if you will, right? So this data forwarded here is just the result of the previous iteration, n-1, but we will also need n-2, right? And then we will get it from here. Basically, we will forward this value here and then copy it. So I will put a copy here. And then this copy is copying the value here and also here to this branch logic. And this branch node is, so this is the false pad, and then this is the true pad, which generates value for other iterations. So this hard-coded 0 will apply only once in the first iteration. Okay, so this is kind of ugly, but here we have copy node, and then this gets 1 in the first iteration, and otherwise gets a token from here, from this pad. Okay, so is there anything that we're missing? One thing we are missing is this, so we haven't connected this here, which is like continuously generates n-1 for each iteration. So this should go here as the data input of this branch. And I think we have all other paths handled. Okay, so let's test the case where n equals 2. How much time do we have? Okay. So I hope I'll finish like in 5 minutes. Okay, so let's just test the n equals to 2 case. I think we already verified n equals to 0 and 1. It should be obvious here. Okay, so for n equals 2, so we start from here, right? So this is the only place where we have a token ready to execute, right? So this is n, which is 2. We know this is 2. And then, so this is being consumed by this copy node, right? So I'll just show it like this. So this is also forwarded here. So we have 2 on those 2 places. And then this node is also ready to fire because it has all its inputs ready. So we have here streams of zeros, and then here we have 2. And then this node will consume this 2 and will generate true, right? Because 2 is greater than 0. And then this node is also ready to fire, and then we will copy true here, and then we will also copy true here. Okay, so we have the flag here, T. We have data 0. So this node is also ready. So we'll consume T here, and also this stream of zeros. And then since this is true, this will do nothing, right? Because it's connected to ground. So basically, this thing will like terminate here and will not be used for the rest of the iterations. Okay, and now what happens is, what else we have ready here?
How come that branch in the top left has 3 inputs?
This one? Yes, it shouldn't have 3 inputs. So basically here what I tried to show is those 2 data inputs are connected to each other, right? So it's just a shortcut. So basically a token either comes from this path, from this copy node, right? Or from this copy node. So in this case, for the first iteration, it comes from this copy node, right? So we have 2 as data here. We have true as a flag here. So we can also consume those 2 values over here. And then when this branch node fires, it will forward 2 here on this path, right? And then we have 2 and -1. This is also ready to fire, and this will calculate 1. So we get 1 here. And then we copy 1 here, and then we copy 1 here, right? So this time, we receive data from this path. And this path is not producing anything anymore. Okay, and then we consume this 1. This again generates true. And then we copy this true here. We copy true here, right? So initially we had 0 and 1 here for this addition. So we consume those 2. This is 1. The result is 1. And then this branch node is ready. We consume those 2, and from the true path, we get 1 here. So this was copy node, and then copy node copies 1 here, and then copies 1 here, right? And then this branch is ready, so we consume the true and 1, and forward 1 from the true path. So this addition in the next iteration, the current iteration, gets 1 and 1, right? So previously it was 0 and 1. So it's 1 and 1, and then this is being consumed. We get 2 here. Okay, so actually we found our answer, but this is not directed to the output yet, right? Because we don't have the flag ready here yet. So we need to propagate the flag. So yeah, I guess we forgot that path. So here, this flag should also be connected here, right? So it's same as the data. So as data receives the token from like 2 different paths, so the flag is doing, right? So here the flag was true, so we get that true here, right? And then this true is being consumed, so basically 1 is forwarded here, and then 1 minus 1 is 0, right? And then 0 gets here, and then it gets copied here, and also gets copied here. So this time, this comparison node generates false instead of true, right? And then this false is copied here and also here. Sorry, this is false, right? And then since this is false, this is grounded and it's not generating any more tokens here on this pad, right? And then we have false here, and then this false is forwarded here, right? Which is again grounded. So this just consumes this with whatever data is here. And then we also copy this false here. And we had 2 as a data here, right? And this is the false pad. So we basically forward this 2 here to the output. And we get 2 for a case where n is 2. So this data flow may not be like very obvious at first, but basically you need to iterate yourself with different values and maybe try different implementations. But the main thing that you need to get from here is that concept of producer and consumer, right? So a token can only fire, a node can only fire if all of its input tokens are ready. Otherwise, it cannot fire. Yes?
On the top left, we have the regular that node. We connected the output to the data into the branch.
tag.
Here, you mean?
Yes.
This part? Okay, we could. Yeah, so this is the flag part, right? Oh no, okay, yeah, okay. I guess you're right. So this basically should be connected here. Is that what you're saying?
Yeah.
Okay, yeah. Okay, I guess, other questions? Okay, then we can move to, oh, question?
Concept correctly, so the inputs like 0 and 1, they can only use 1, right? Or like, how do I decide which to use
Yeah, I mean, so here in this notation, it's not clear, but so you can do that in a data flow engine. You can define to have like constant stream of some value, right? So here, I think I explained like that. So here we have streams of zeros. So I will show it like the 0 ... So it continuously gets 0 tokens from this input, right? But those are just one-time values that are being generated only once when you initialize your data flow engine. So same here, this is also ... And same here, -1. Okay, so those are all streams, but those are initial values, this 0 and this 1. So this is also stream. I guess we need to make the notation more clear. Okay. Okay, I think we'll continue with other questions.
Yeah, in the remaining time, we have 8 more minutes. We will talk briefly about one of the GPU questions that you have in homework 5. If I find it. Yeah. So this is like typical question in which you have to calculate what's the SIMD utilization. Remember that the SIMD utilization, not only in GPUs, but also in vector processors, mean like the ratio of lanes that you're actually using. So here, the first thing that you have is the definition. SIMD utilization of a program run on a GPU is defined as the fraction of SIMD lanes that are kept busy with active threads. When are we going to have active threads? Well, we're going to have active threads when we actually execute some instructions for these threads. The question gives us some piece of code, and this is essentially a for loop, as you can see. And it says that this is going to be executed on a GPU. So the way that this is going to be executed on the GPU is distributing the iterations of this loop across the threads that we have in warps. So here we have n iterations, and these n iterations are going to be executed by a certain number of warps. That's the first question, that's part A. How many warps does it take to execute this program? Please leave the answer in terms of n. So we have n iterations. We know that the warp size is 32. A warp in the GPU consists of 32 lanes, and we also have, 32 threads, and we also have 32 SIMD lanes in the GPU. So n divided by 32 is the number of warps, because, so in case that n is not divisible by 32, we have to use the ceiling of this division, right? Maybe the last warp is not completely busy, but we will steal this number of warps. Part B says, assume integer arrays A. So we have A and B. A has a repetitive pattern with 24 ones, so it will be something like this, 24 ones, followed by 8 zeros. And B have a different repetitive patterns which have 48 zeros followed by 64 ones. What's the SIMD utilization of this program? So observe that this is the repetitive pattern of A. And A, the values of A determine if the body of this if statement is executed or not. As you already know, this if statement will be converted into some kind of comparison and some kind of branch, right? Because in case that you don't need to execute this body, you will have to branch in order to avoid this loop body. So that's why depending on what's the exact value that each of the 32 threads of the warp read, we will execute the body of this if statement or not. And observe that here the condition is that A is divisible by 3. Because all these 24 ones that we have here are not divisible by 3. Only those threads that read I equal 0 will actually execute this statement here. So, if we have two instructions, instruction 1 and instruction 2, the first instruction for sure is executed by 32 threads, but the second in each warp, right? But the second instruction, instruction 2, is only executed by those threads for which A modulo 3 is equal 0. That is, for these 8 threads that read these 8 zeros here. So, out of 32 plus 32, that would be the maximum number of threads that we have executing this instruction 1 and then instruction 2, threads that belong to the same warp. The SIMD utilization in this case is 32 plus 8 divided by 32 plus 32. So this is 40 divided by 64. So that's the answer to this part B. The second part says, is it possible for this program to yield SIMD utilization of 100%? Well, and the answer is yes. But this case in which the SIMD utilization is 100% is going to be dependent on the value of each of the elements of register of array A, as you already know. There are two possibilities here if we want to have 100% SIMD utilization. The first possibility is that all threads in each warp execute instruction 1 and then they go into the body of the if statement and they execute instruction 2. That's one possibility. The other possibility is that the threads in the warp, all the threads in the warp execute instruction 1, but they don't execute instruction 2 because this if condition is not true for any of them. So the answer in this part, if yes, what should be true about arrays A for SIMD utilization to be 100%, the answer here is two possibilities. Every 32 elements is divisible by 3, or every 32 elements isn't divisible by 3. So either way, we will have all threads in the warp executing both instructions or only executing one of the instructions. We are going to stop here because we run out of time. The rest of the exercise is very similar. You already know how you have to reason about this exercise. Here, there is a question, part D and E are very similar questions, but the percentage, the SIMD utilization is different. You can reason in a similar way. And the very last part is actually quite easy. This is what we explain in the GPU, the first GPU lecture about dynamic warp formation. You might remember that there might be a way of, let's say, merging warps like this, where some threads are active, other threads are not active, and if these threads that are active are not, in different warps, are not in the same lane, they can be merged, and this way we can have more efficiency in our execution. We stop here. Thank you very much for your attention, and enjoy the holiday.